In 2003, archaeologists unearthed human remains in Ethiopia that would shake the foundations of our understanding of human evolution. The discovery was so groundbreaking that it forced scientists to rewrite textbooks and rethink the entire timeline of our species. Welcome to Arnie's Brain Train, where today we're uncovering a 195,000-year-old secret that rewrote human history. For decades, scientists believed modern humans, that's us, Homo sapiens, first appeared around 100,000 years ago. This wasn't just a random guess. It was based on numerous fossil discoveries across Africa, Europe, and Asia that seemed to tell a consistent story. But hidden beneath the dusty soil of Ethiopia's Omo Valley lay the evidence that would double that timeline. The story begins in the early 2000s when an international team of researchers led by Tim White ventured into the remote Omo Kibish formation in southwestern Ethiopia. This region is a part of the Great Rift Valley, a vast geological feature stretching from Lebanon to Mozambique, created by the separation of tectonic plates over millions of years. The Rift Valley has long been a treasure trove for paleoanthropologists because its unique geology has preserved remains from virtually every stage of human evolution. This harsh, unforgiving landscape seems like an unlikely cradle for humanity. Today, the region is characterized by extreme temperatures and sparse vegetation. Yet, it's precisely here where our oldest ancestors left their traces. The area around the Omo River would have looked very different 195,000 years ago, with periods of lush vegetation alternating with drier phases as the climate fluctuated. The expedition itself was a massive undertaking. The team spent weeks navigating difficult terrain, camping in remote areas, and methodically surveying the landscape for any signs of fossils. They used satellite imagery to identify promising sites, focusing on areas where ancient sediment layers had been exposed by erosion. One afternoon, a team member spotted something unusual protruding from a weathered hillside, what appeared to be fragments of a human skull. In the scorching heat, the team carefully extracted these fossilized skull fragments, meticulously cataloging their exact positions and the surrounding soil layers. It wasn't until months later, after careful cleaning and reconstruction in the laboratory, that the true significance of the find began to emerge. The skull showed distinctly modern features, a high rounded forehead, reduced brow ridges, and other characteristics that define Homo sapiens. But when the surrounding ash and sediment samples were later dated, using advanced radiometric techniques, the results left scientists stunned. These weren't just any human fossils. They were the remains of fully modern humans who lived 195,000 years ago, nearly twice as old as previously thought possible. The team double-checked their results, sent samples to independent laboratories, and scrutinized every aspect of their methodology. But the conclusion remained inescapable. Modern humans had existed much earlier than anyone had imagined. The discovery was named Omo 1, and it wasn't completely alone. Another partial skull, later named Omo 2, was found nearby, but showed some more primitive features, highlighting the complex mosaic of human evolution happening at this crucial time. Now, you might be thinking to yourself, how can a scientist actually be so confident about the age of these bones? It's not like they come with a tombstone or a birth certificate. So, when we talk about something being 195,000 years old, that's an incredibly precise claim about events that occurred long before written history. The dating process primarily uses something called argon-argon dating, which is a refined version of the better-known potassium-argon method. This technique relies on a fascinating property of radioactive elements. They decay at absolutely predictable rates, regardless of temperature, pressure, or chemical environment. When volcanic eruptions occur, they release minerals containing these radioactive elements. As the volcanic material cools and solidifies, these elements become trapped in crystals, and the radioactive clock starts ticking. Specifically, the method focuses on the decay of potassium-40 into argon-40. Potassium-40 has a half-life of 1.25 billion years, which means that after that time, half the original potassium-40 atoms will have decayed into argon-40. By measuring the ratio of these isotopes in volcanic materials, scientists can determine when an eruption occurred with remarkable precision. The Omo Kibish Formation contains numerous layers of volcanic ash and tuff, compressed volcanic debris, interspersed with sedimentary layers where fossils might be found. Think of it like a giant layer cake, with each layer representing a different time period. The human fossils were sandwiched between two such volcanic layers, providing an ideal scenario for dating. By measuring the ratio of different argon isotopes in the volcanic layers above and below the fossils, scientists can determine when these eruptions happened. And since the fossils were sandwiched between these layers, their age must fall somewhere in between. In the case of Omo 1, the volcanic layer just below the fossils was dated to about 196,000 years ago, while material above was younger, establishing that the human remains must be around 195,000 years old. But good science never relies on just one method. To increase confidence in their dating, researchers employed multiple cross-checking techniques. They analyzed the sediment layers using stratigraphy, the study of rock layers, to ensure that the site hadn't been disturbed. They examined other fossils found in the same strata, remains of animals whose timeline is already well established. They also cross-referenced with paleoclimate data. What really makes this discovery particularly reliable is that multiple teams have independently verified the findings. When the initial dates were published, some scientists were skeptical, as they should be with any revolutionary claim. Several independent laboratories subsequently analyzed samples from the site using slightly different techniques. The consensus strongly supports the original dating. It's also worth noting that dating ancient specimens is always subject to some margin of error. The published date for Omo 1 is actually 195,000 years plus or minus 5,000 years, meaning scientists are confident the true age falls somewhere between 190,000 and 200,000 years ago. This range reflects the inherent limitations of dating methods, but even at the youngest end of this range, Omo 1 still significantly predates what was previously thought to be the oldest Homo sapiens. So what did these ancient people actually look like? Would you recognize them if they walked past you on the street today? Could they blend into a modern crowd if given contemporary clothing and a haircut? The answer might surprise you. Despite living nearly 200,000 years ago, these individuals had the same basic anatomy as modern humans. Their skulls showed the distinctive high rounded forehead, small brow ridges, and presence of a chin that characterize Homo sapiens. These features might seem unremarkable to us today, but they represent a dramatic evolutionary shift from earlier human species. To appreciate just how modern the Omo 1 individual was, we need to compare them with other human species that existed around the same time. Unlike our Neanderthal cousins with their robust builds, long low skulls, prominent brow ridges, and receding chins, these ancient Ethiopians had the lighter build and facial structure we associate with people today. While Neanderthals were adapted to cold European climates with their stocky bodies, large noses, and shorter limbs, the Omo individuals show the more gracile or slender build and the longer limbs that are adaptations to warmer climates. Their brain cases were fully modern in size, meaning that they had cognitive abilities similar to our own. The average brain volume of modern humans is about 1,350 cubic centimeters, and the reconstructed cranium of Omo 1 falls well within the normal range for modern populations. However, they were still likely more robust than the average person today. stronger with denser bones and more pronounced muscle attachments. Life was physically demanding, and their bodies reflected that reality. Imagine an Olympic athlete, someone with exceptional strength and endurance, rather than the average person today. Their teeth would have likely been larger and showed more wear than modern teeth. Without processed foods, dental hygiene, or dental care, their teeth would have experienced more stress from chewing tough foods and might have been used as tools for processing materials. As for skin color, hair type, and other soft tissue features, these cannot be directly determined from fossilized remains. However, given the geographic location and what we know about human adaptation to UV radiation, it's reasonable to infer that these early Ethiopians would have had darker skin, which provides protection from the intense equatorial sun. DNA analysis has been challenging due to the age and condition of the fossils. Ancient DNA rarely survives in hot, humid environments like those found in much of Africa. However, what little genetic information scientists have extracted suggests that these individuals belong to lineages that contributed to all non-African populations today. More recent genetic studies of contemporary human populations support this connection. By analyzing the rate at which mutations accumulate in human DNA, geneticists can create a molecular clock that points to when different populations diverged from one another. These genetic studies consistently show that all non-African populations share a common African ancestor who lived approximately 200,000 years ago, remarkably consistent with the Omo Kibish dating. If we could bring an Omo individual forward in time and give them modern nutrition, healthcare, and education from birth, they would likely function indistinguishably from any modern human. Their capacity for language, abstract thought, creativity, and learning would be identical to our own. So what was life like 195,000 years ago? What would you see? What world did these ancient humans inhabit? The environment around the Omo River then was quite different from today. East Africa experienced dramatic climate fluctuations during this period, oscillating between wetter and drier phases driven by changes in Earth's orbit and tilt, what scientists call Milankovitch cycles. During wet phases, the landscape transformed into lush grasslands and forests teeming with wildlife. The Omo River would have been fuller, perhaps creating extensive wetlands and floodplains rich in resources. During drier periods, the landscape would have resembled modern savanna, open grasslands with scattered acacia trees and shrubs. The animal life surrounding these early humans would have been both familiar and strangely different. These humans shared their world with several species now extinct or locally extirpated. Massive prehistoric elephants, including Elephas rechi, straight-tusked elephants, that stood taller than modern elephants, roamed the savannas. Giant buffalo, Pelorovis, with horn spans reaching up to 3 meters or 10 feet across, grazed the grasslands. Various species of big cats, including some larger than modern lions, would have been apex predators alongside early humans. Giraffes, various antelope species, zebras, and rhinoceroses populated the grasslands. Many of these would have been important prey animals for human hunters. The rivers teemed with fish, crocodiles, and hippos, providing additional food sources. But life wasn't easy for these early humans. They faced a constant challenge unknown to most of us today. Predators posed a genuine threat. Large carnivores like lions, leopards, and hyenas would have seen humans as potential prey. Without permanent shelters, people would have been vulnerable, especially at night. These early humans faced drastic climate shifts that could transform their environment in the span of a generation. During dry periods, food and water became scarce, forcing them to adapt their behavior or migrate to more favorable regions. Disease would have been another constant threat. Without modern medicine, even minor infections could prove fatal. Parasitic diseases like malaria, which is endemic to parts of Africa, would have affected communities. Dental problems, bone fractures, and other injuries would have been common and often debilitating. Evidence suggests that they were hunter-gatherers who developed sophisticated stone tools. Archaeological sites from this period reveal tools created using the levallois technique, a method of knapping stone to create flakes with predetermined shapes. These tools included points that might have been attached to wooden shafts as spears, scrapers for processing animal hides, and cutting tools for butchering game. They lived in small, highly mobile groups, perhaps 20 to 50 individuals comprising several family units. These groups would have been constantly on the move, following seasonal resources and developing intricate knowledge of their environment. Their survival depended on cooperation, communication, and cultural knowledge passed down through the generations. Intriguingly, some evidence suggests that they may have used pigments, possibly for body decoration or symbolic purposes, hinting at the early emergence of symbolic thinking that defines human culture. At several sites in Africa dating to this period, archaeologists have found lumps of ochre with scratch marks indicating deliberate use. This suggests that even 195,000 years ago, humans were engaging in behaviors that went beyond mere survival. Now, let's shift to our evolutionary cousins, the Neanderthals. For a long time, scientists debated whether Neanderthals were our ancestors or a separate branch of the human family tree. The discovery of these 195,000-year-old Homo sapiens helps to clarify this relationship. Both modern humans and Neanderthals evolved from a common ancestor that lived much earlier, possibly around 700 to 500,000 years ago. This common ancestor was likely Homo heidelbergensis, a species that spread across Africa, Europe, and parts of Asia. In Europe, isolated populations evolved into Neanderthals, adapting to colder conditions with stockier builds and larger noses. Meanwhile, in Africa, a different evolutionary path led to modern humans, with higher, rounder skulls and more gracile builds. For hundreds of thousands of years, these two human species, Neanderthals and Homo sapiens, developed separately, adapting to different environments and creating distinct cultural traditions. Neanderthals became supremely adapted to the cold environments of Ice Age Europe, developing technologies like hafted spears for close-quarter hunting of large game. But here's something interesting. DNA evidence shows that when modern humans later expanded out of Africa, approximately 60,000 years ago, they encountered and interbred with Neanderthals. This interbreeding wasn't a rare event. It appears to have happened multiple times as modern humans spread across Eurasia. Today, most non-African populations carry about 1 to 4% Neanderthal DNA in their genomes, a genetic legacy of these ancient encounters. This genetic interchange reveals something profound about these two populations. Despite having evolved separately for hundreds of thousands of years, they were still similar enough to produce fertile offspring. The Neanderthal genetic contribution wasn't just a neutral leftover. Some Neanderthal genes appear to have provided advantages to modern humans expanding into new environments. For example, certain immune system genes may have helped our ancestors combat pathogens they encountered outside Africa. Other Neanderthal genes influence skin and hair color, potentially helping humans adapt to different UV levels at higher latitudes. Not all Neanderthal DNA was beneficial, however. Studies show that Neanderthal genes associated with certain diseases are still found in modern populations. Additionally, Neanderthal genes appear to be largely absent from the X chromosome, suggesting that hybrid males may have reduced fertility. So, while Neanderthals weren't our direct ancestors, they are definitely a part of our family, more like cousins than parents. The 195,000-year-old Ethiopian fossils represent a purely Homo sapien lineage before any Neanderthal interbreeding occurred. The Omo Kibish discovery forced scientists to completely rethink the human timeline. If modern humans existed 195,000 years ago, many other assumptions about human evolution needed a revision. Prior to this discovery, the prevailing theory suggested humans evolved recently and rapidly. The fossil records seem to indicate that modern features appeared suddenly around 100,000 years ago, suggesting a rapid evolutionary transition, perhaps driven by genetic mutations affecting brain development or language. Now, it appears our species has a much deeper history, with more time to develop the complex behaviors and adaptations that define us. The extended timeline suggests a more gradual emergence of modern features and behaviors, with different populations evolving at different rates. This longer timeline has also solved another puzzle. Genetic studies had consistently suggested modern humans emerged earlier than the fossil record indicated. When geneticists analyzed the rate at which mutations accumulate in human DNA, creating a sort of molecular clock, they consistently calculated that modern humans must have emerged around 200,000 years ago. The Omo Kibish fossils helped reconcile these two lines of evidence. This discovery also strengthened support for the out of Africa theory, the idea that all modern humans descended from African ancestors who later migrated to other continents. With definitive evidence of Homo sapiens in Africa nearly 200,000 years ago, long before they appeared elsewhere, the African origin of our species became even more certain. The new timeline also created space for understanding the complexity of human migration patterns. Rather than a single exodus from Africa, it now appears that there were multiple waves of migration, with early populations moving into the Middle East perhaps as early as 180,000 years ago, as evidenced by fossils discovered in Israeli caves. This revised timeline also sheds light on the development of behavioral modernity, the suite of behaviors including complex language, symbolic expression, artistic representation, and technological innovation. Archaeological evidence from sites across Africa suggests that elements of behavioral modernity emerged gradually, with evidence of symbolic thinking appearing in some populations by 100,000 years ago or earlier. Finally, the extended human timeline has implications for understanding human genetic diversity. The longer a population exists in a region, the more genetic diversity it accumulates through mutations. This explains why African populations today show greater genetic diversity than populations elsewhere. They represent the original human population that has been accumulating variations for nearly 200,000 years. Despite the importance of the Omo Kibish discovery, enormous gaps remain in our understanding of early human history. The fossils give us a tantalizing glimpse into our distant past, but they also highlight how much we still don't know. One of the most significant unanswered questions is exactly when and where the first anatomically modern humans appeared. While the Omo fossils push this date back to at least 195,000 years ago, they likely don't represent the very first members of our species. Some fossils from Jebel Irad in Morocco show a mix of archaic and modern features dating to around 315,000 years ago, suggesting our species might be even earlier. We also don't know what precisely drove the evolution of modern human features. Was it adaptation to specific environmental conditions, changes in diet, social or sexual selection? Without a time machine, reconstructing the selective pressures that shaped our species remains challenging. The cognitive and behavioral capabilities of these early modern humans also remain somewhat mysterious. When did humans develop complex language? When did symbolic thinking and artistic expression become widespread? The archaeological record from this period is sparse, making it difficult to reconstruct the mental and cultural lives of our distant ancestors. Another major question concerns population structure. The fossil and genetic evidence suggests that early humans lived in relatively isolated populations that occasionally connected through migration and interbreeding. But the details of these population dynamics, how many distinct groups existed, where they were located, how often they interacted, remain to be fully understood. The relationship between climate change and human evolution also requires further investigation. Climate records show dramatic fluctuations during this period, with alternating wet and dry phases affecting resource availability and habitat suitability. These climate shifts likely influenced human migration patterns and adaptations, but the precise mechanisms linking climate change to human evolution are still being explored. And perhaps most fundamentally, we still don't fully understand why Homo sapiens succeeded while other human species ultimately disappeared. Our species wasn't necessarily stronger, smarter, or better adapted than contemporaries like Neanderthals. Yet, we survived and spread across the globe while they vanished. Was it luck? Superior technology? More effective social organization? The answer likely involves multiple factors, but determining their relative importance remains challenging. The 195,000-year-old humans of Omo Kibish may have lived in a world vastly different from our own, but they were us, anatomically modern humans with the same capacity for language, art, and complex thought. Their discovery connects us more deeply to our past and reminds us that our history extends far beyond what we once imagined. When we consider the immense challenges these early humans faced, predators, climate change, disease, and the daily struggle for survival, their resilience becomes all the more remarkable. Without modern technology or stable food supplies, they not only survived, but thrived enough to eventually populate the entire planet. The story of the Omo Kibish discovery also reminds us of the contingent nature of scientific knowledge. What we know is always subject to revision based on new evidence. Science progresses not through rigid adherence to established ideas, but through a willingness to reconsider fundamental assumptions when new data demands it. Perhaps most importantly, the Omo Kibish discovery reminds us of our shared humanity. Despite the tremendous diversity among modern human populations, differences in appearance, language, culture, and technology, we are all members of a single species with a common origin in Africa. The differences that sometimes divide us emerged relatively recently in our evolutionary history and are literally skin deep compared to our shared biological and genetic heritage. Understanding our deep past gives us perspective on our present. Some of the challenges we face today are not entirely unlike those of our ancestors, albeit at different scales and with different technologies at our disposal. Well guys, this has been Arnie's Brain Train. Thank you for letting me take you on this journey through the hidden chapters of human history. If you enjoyed this deep dive into our ancient past, please hit like and subscribe for more mind-expanding content that challenges what you thought we knew. Leave a comment with what aspect of human evolution you'd like to explore next, maybe Neanderthals, Denisovans, or the mystery of when humans first tamed fire. All of our sources are in the description below. And until next time, keep your brain on track and your curiosity flowing. Bye guys.